Let's resolve the second example using fixed base method. You are watching hydrology. When we draw a hydrograph, there will always be two parts of the water. The one on top is the direct runoff, which we can use to run our water projects. And the one at the bottom is the base flow, which is the amount of water underneath the grade replenishing streams and rivers. How does fixed base method separate the base flow? Using the same hydrograph, where the x-axis is time and the ordinates are discharge, draw the distribution curve from the given dataset. After knowing the start of the runoff, extend the line or curve right before the start of runoff. The extension touches the peak discharge. With the intersection at the peak discharge, connect the point to the end of runoff. So from the output, fixed base method includes two slopes separated by the peak discharge data. The problem includes 14 data points from 14 days of record. The highest flow is on the second day, and the area of catchment is 5,033 square kilometers. The initial step is to plot the points from the dataset. There are 14 days in the x-axis, and also the highest yield is 35,000, which requires the ordinate to reach that value, so we use 7,000 increments. After plotting the 14 points in the hydrograph, connect them to have the curve. This curve shows the peak discharge is at T of 2 days, with ordinate of 34,300. Also identify the start of runoff, which is at T of 1 hour, with ordinate of 2,340. With fixed base method, we place a line from T of 1 day. Without any antecedent, we use the horizontal line extended until the peak discharge. The location of the end of runoff, though, is a little unclear. Thus, use the formula to find it. With n as 0.826 of the area raised to 0.2, the end of runoff is taken as 0.826 times 5,033 raised to 0.2, which is 4.543 days from peak discharge. This is like at T of 6.543 because the peak discharge is at T of 2 days. Connect the separator from peak discharge to the end of runoff. To identify the ordinate at the end of runoff, use similar triangles. From the illustration, take the small triangle with ratio of y is to 0.457 and proportion this with the big triangle having 1,440 is to 1. Y is then simplified as 658.08. Thus, the ordinate at T of 6.543 is 4,300 plus 658.08, which is 4,958.08. Next is to compute for the base flow for those intervals included in the second extension line. The difference of y per day is computed as 2,618.08 over 5.543, which is 472.32. The base flow at T of 3 days is the reference height of 2,340 plus 472.32, resulting to 2,812.32. The fourth day has a base flow of 2340 plus twice of 472.32, simplified into 3281.64. On the fifth day, this has the ordinate of 2340 plus thrice of 472.32, which makes 3756.96. We can then tabulate the base flow for each day. At day 1, the total flow is all considered as base flow. On the second day, the base flow is taken as 2340 as the first extension line is drawn horizontally until the peak discharge because of insufficient points before the start of runoff. From the third day until the fifth, the base flow values are computed as 2812.32, 3281.64, and 3756.96. The sixth day onwards have the total flow considered as base flow. To answer the requirement, add another column for direct runoff. The first day has 0 DR, as all total flow goes to base flow. On the second day, direct runoff is 34,300 minus 2,340, resulting to 31,960. The third day has direct runoff of 22,187.68 from 25,000 minus 2,812.32. The fourth day has 14,000 less 3,281.64. That is 10,718.36 cumex. Then on the fifth day, there is a base flow of 3,756.96 subtracted from the total flow, leaving 5,203.04 direct runoff. The rest of the days on record leave 0 direct runoff, as all total flow is considered as base flow. The summation of direct runoff comes out as 70,069.08 cumex. To take the volume of runoff, multiply the time, which is 24 hours, with the summation. Then convert it into seconds. The seconds and hours cancel out, thus leaving the volume of direct runoff as 6.05397 megacubic meters.